Hi guys, so today I'll be going over the questions of the April long challenge recently conducted on CodeChef. I'll start off with the first question, COVID LQ. So yeah, as this is the first question, this is the easiest question and I'll move on to the harder questions later on. So I'll give you a gist of the problem statement of each question. In this question, we are given t number of test cases in the input, n integers, and then a line that contains n integers a1, a2, an. Now, what a actually is like a queue or a line which has zeros and ones. So, if a position is equal to 1 in the queue, that is a person is standing there in the queue. If it is 0, that means it's an empty position in the queue. What we have to see is, are people following the rules of the COVID pandemic, which is to stay at least 6 feet away from each other. So what we basically have to check is, are the consecutive ones, that is the first appearance of 1 and the second appearance of 1, 6 feet away, the second appearance and the third appearance are 6 feet away. If any one single consecutive appearance of ones is less than 6 indexes away, we will say they're not following the rules. So I will be writing my code in Python, but I will explain to you how to do it in C++ as well if there is a difference logically. So first, this is the loop for the test cases. Then I'll take n input, that is the number of integers in the array. Then I will take that array or list as input. So then I will be initializing a list, which is basically a vector in C++, as an empty one, and then I will run a loop for n over a. If I find a 1 in that position, I will store the 1, I will store the index in L. So I now have every position of 1 in the array. So what I basically have to check is are the consecutive ones 6 feet away from each other. So for that I will initialize a variable flag which will be equal to 0. Then I will run a loop len of L times minus 1, as we do not have to check after the last element. So if if L of I plus 1 minus L of I, that is the consecutive ones, are less than 6 indexes away from each other, we will put flag equal to 1 and we'll break out the loop. Now if flag equal to 0, that is it never entered this if condition, and that means that there are no particular ones that are 6 feet away from each other. What we'll do is we'll print yes, they're following the rules of the COVID pandemic, else we will print no, they're not following the rules. So yeah, a very simple approach to a very simple problem. I'll move on to the next one. Okay guys, so the second problem is sell all cars or car sell. The gist of this problem is that chef owns n cars and he wants to sell all of them over n years, that is one car each year, and the price of each car decreases by 1 unit per year until it is sold. And we have to compute the maximum profit chef can make 10 modulo 10 raised to the 9 plus 7. Now the important thing in this question is this small paragraph, that when the price of a car reaches 0, it cannot drop further and it remains 0 in all subsequent years. So first I'll take the input, which is t test cases followed by an integer n in each test case, and the list p. So as I said, the important thing to note here is that the price of a car cannot drop below 0. Now what you'll notice here is that each year chef makes a loss. Now that loss can be written as I will show you in just a sec. That loss can be shown as n minus year, that is which year it is right now, plus k. Now what this plus k is, I'll explain to you why it is n minus year first. So in the first year chef sells one car and the value of the remaining cars drops, and remaining n minus 1 cars drops by 1 each, that is n minus 1 loss. In the second year he sold another car and the loss now is n minus 2 for all the n minus 2 cars. Now what this plus k here is the number of cars that have already hit value 0, and because they've already hit value 0, we will not incur a loss on those values. So now what we have to do is clear, because we can greedily select the most expensive cars first, as they will not hit 0 until the later years, and the cheapest car will hit 0 first. So what we have to do is greedily select those most expensive car we will sell first, we'll have answer equal to 0 and year equal to 0 at the beginning. We've sorted P, and now we'll run a for loop from the last element of P, which will be at index n-1, to the first element, which will be at index 0, and I'll decrement I on each count by -1. Then we will have answer plus equal to, which is the same thing as answer equal to answer plus something, answer plus equal to max of P of I minus years, right, comma 0. That is, if P of I minus year is less than 0, then we will have 0 profit for that car. Now this, as I said, this will be the same as this statement here, comma 0. So then we also have to do one more thing in this for loop, that is increment year by 1, because next year will be 1 minus 1 on the car we sell that year. And then we'll just print answer modulo 10 raised to the power 9 plus 7, and that will be your answer for this question. So the third question is strange numbers. We are given two numbers, x and k. What we need to determine is if there is an integer a that can exist with exactly x positive integer divisors, that is x factors, of which exactly k are prime. Now the key to solving this question is to find the relationship between the number of prime factors and the number of total factors. Say a number a has prime factorization such as a1 raised to the power p1 into a2 raised to the power p2 into an raised to the power pn. Then the number of factors this number would have is p1 plus 1 into p2 plus 1 up till pn plus 1. Say for a number 24, it can be prime factorized as 2 raised to the power 3 into 3 raised to the power 1. So the total number of factors for this number would become 3 plus 1 into 1 plus 1, which is 8. So the 8 factors of 24 are 1, 2, 3, 4, 6, 12 and 24. Okay, so now we'll take the input for this number for this problem, which is just x and k over all test cases. Okay, so now as I said, the important thing to note here is how to write this. So what you can see is this will be the factorization of the number of factors. Now when the maximum number of, now the number of elements in this is k, and it will be maximum if all k of them are prime. But say if one of them is composite, you can break that down into prime factors and increase the number of factors. So first we will find out the prime factorization of x and see if it has at least k factors. If it has at least k prime factors or more, that number can exist, as it can be shown as this for k numbers. It can be shown as it is greater because you can take as 2 into 2 into 3, you can explain that as 4 into 3 or 2 into 6. So now we'll make a function that will calculate the number of prime factors a number has. So how we'll do that is we'll initialize num equal to 0, that is the number of prime factors, and while x modulo 2 equal to 0, we'll add num plus equal to 1, x equal to x by 2. Then we'll run a for loop from 3 to the square root of x, which is x raised to the power 0.5. And why I have taken this 2 separately is because 2 is the only even prime factor. So now here we can skip each indentation by 2. So we'll save a little bit of time on the program. While x modulo I equal to 0, num plus equal to 1, x equal to x by I. Now it is also possible that the number itself is a prime number. So what we'll check is if x is greater than 2 now, we will add num plus equal to 1. So now this here will give us the total number of prime factors of x. So we'll take a h equal to prime factors of x. Now as I explained to you earlier, this here can be shown as a factorization of x, and it will have k elements. So if the prime factorization of x has greater than equal to k elements, it can be shown as a product of k primes. So we'll see if h is greater than equal to k, we'll print 1, the number can exist, else we'll print 0. And that's what you have to print here. For each test case, print a single line containing one integer if a valid integer a exists, or 0 if it does not. Okay, so the next question we have is unit GCD. The gist of this problem statement is chef has given a book which contains n pages numbered 1 through n. What chef wants to do is read all of these pages, but there is a condition on the pages he can read in one day. So the condition here is chef can choose to read any set of pages such that there is no prime that divides the number of 2 or more of these pages. What that means is that for any 2 pages that he reads in a day, the greatest common divisor GCD or HCF, highest common factor, will be 1. So for example, for 1, 3 and 10, for 1 and 3 it is 1, for 3 and 10 it is again 1, and for 1 and 10 it is also 1. So this is valid. He can read 1, 3 and 10 on the same page. But for say 1, 3 and 9, he cannot read it because 3 and 9 have a common factor of 3, which is greater than 1, which is a prime that divides both of these numbers. Okay, so since chef might get bored by reading the same recipe again and again, chef will read every page exactly once. So we cannot repeat the pages. What we have to find out is the minimum number of days chef needs to read, and the book and the to read the entire book, and the pages chef should read on each of these days. Now how we have to give output is print the number of pages, and then print for each day how many pages he is reading and the number of those pages. So on the second day he is reading 2 pages numbered 3 and 4. Now what some people might think of a solution for this is that for one page he needs 1 day. For 2 pages he also needs 1 day, as 1 and 2 are co-prime. Similarly for 3 pages he also needs 1 day, 1, 2 and 3 are co-prime. But for 4 he needs 2 days, as 2 and 4 are not co-prime. For 5 again he needs 2, as 4 and 5 are co-prime, they can go in the same one. For 6 he needs 3, as one day already contains 2 and 1 day already contains 4, so 6 needs to go in a separate day. Now what some may do is calculate it for every I number of days from 1 to 10 raised to the power 6, which are the given constraints. But to check co-prime with all other numbers in that day will take a lot of time, so that will give time limit exceeded, so this dynamic solution will not work. What some others might do is greedily select them, so they will put all the prime numbers in one day, because no prime numbers will have a common factor because they are prime, they only have one and the number itself as a factor. But that again would not work, as they would have to do the other pages, and there is a little difficulty finding the logic for that. Now what I did here, as you can see, is 7 would also require 3 days, as it can fit in with 6. Now you may be noticing a trend here. The number of days is increasing whenever the number of even number increases, except for 2 here. That 6 increases, it will be 3, and again for 8 it will be 4. Because n by 2 of the n numbers from 1 through n would be even, and they will have a common factor of 2. So we would require at least n by 2 days. So at least n by 2 days. Now what that means is n by 2 here is floor division of 2, as 5 by 2 is also 2. So as it is floor division, all we have to do is find one more number to pair with an even number in these n by 2 days, and then chef can read all the pages. So I'll start out by taking the input, which is first the number of test cases, and secondly it is an integer n, which denotes the number of days. So as 1 is a special case, I will write it as follows. print 1. He requires one number of day where he will read one page which is numbered 1, and I'll write 2 also as a special case, because it is the only even number where the number of days are not increasing, as you can see, as 9 would require 4 and 10 would require 5 number of days. So I'll write 2 also here as a specialized case. He'll be reading 2 pages on the first day, 1 and 2. Okay, so now as we have determined n by 2 is floor division, I'll print n by 2, which will be the floor division. In Python this is directly the floor division, so is it in C++, I believe. Okay, so then I will run a loop from 2 to n plus 1. This will terminate at n, where each time I has been incremented by 2. So for the first day, as I've already entered these two conditions where I'll add continue, so the code does not continue further after printing, I know that at the very least n here is 3. So I will print if I equal to 2, I will print 3, 1, 2 and 3. So as I know that at least 3 number of days in each. What that allows me to do is start every iteration with an even number. As I've skipped 3 here, first day is a special case requiring 3 pages. After that I can skip to 4, then 6 and so on. Now what you also may be noticing is the number of days does not increase when the odd number comes in. What that means is we can always pair I and I plus 1 together. I and I plus 1 will always be co-prime and they will have no common factor, as every number that has a factor of 2, it is, by doing sieve you can notice this, it skips one number. So here it is skipping 5, then here it is skipping 7, here it is skipping 3, and similarly for 3 it is skipping 2 numbers, 3, then 6, it's skipping 4 and 5, then it's skipping 7 and 8, and for every number that has a factor of n minus 1 numbers are skipped. So I and I plus 1 we're skipping no numbers, so the only common factor it has is 1. But we also have to check in another condition, that is if the number of pages is even, then we do not have to print I plus 1, because then it would be n plus 1 we would be printing, which would be wrong. So if the number of pages is even and we reach the last page, we do not need to print I plus 1. So if I is not equal to n, that is we have not reached the last page, we will print 2 I plus 1. Else if it has reached n, we will print 1, as we only need to read n. Now if you may be thinking, what if this is odd? But as I have iterated twice here, the ith number will never be odd. If it is n is totally odd, then it will reach n minus 1 at the last iteration, where we'll print this, as I will not be equal to 1, it will be equal to n minus 1, and this will be the solution for this problem. Again, the key thing to notice here was that you would require at least n by 2 days, and after that all you have to do is pair the n by 2 even numbers with one more number. So the next question here is squared subsequences, where we call a sequence good if the product of that sequence here, as you can see s1, s2 and sk, is it is possible to find two integers for this sequence such that the product can be shown as a difference of these two integers square, as p square minus q square. So Chef has a sequence a, a1, a2, an. He wants to find the number of contiguous subsequences of a which are good. So first we'll take a look at what is a contiguous subsequence. For subsequence 1, 3, 5, 4, 2, it will be considered a contiguous subsequence if all the continuous elements of that are taken and no element is missed. So for example 5 and 4 will be 1, 2 itself will be 1, but 3, 5 and then 2 would not be 1, as we have skipped 4. So the total number of contiguous subsequences for a sequence with n integers is n into n plus 1 by 2. Now we have to see what number can be represented as a difference of two squares, because that will be the key to solving this problem. So what numbers can be represented as difference of two squares? So first what we have to see is the square of the nth number is also the sum of the first n odd natural numbers. What I mean by that is the square of 1 is 1 itself, then 1 plus 3 is the square of 2, 1 plus 3 plus 5 is the square of 3, 1 plus 3 plus 5 plus 7 is the square of 4. Right, first 4 odd numbers and it is the square of 4. We can prove this by simply taking an arithmetic progression with a is equal to 1 and d is equal to 2. The sum of this will be n by 2 into 2a plus n minus 1 into d, which if you solve you will easily find out is n square. Now that we have found out this, what this will help us prove is that any odd integer can be shown as a difference of two squares. Because for example, let me take an arbitrary odd integers, say for 6, 7, 8, 9. There will be a square with which can be shown as 6, 7, 8, 7 plus 6, 7, 8, 9. And then the square of the, let's say this is square of k, then k minus 1 square will be this. So if we subtract these two, we obviously get 6, 7, 8, 9, which is an odd number. So for any odd number we can find this as a difference of two squares. Now there is also a case for even numbers, because say 4 square minus 2 square, which will give you 16 minus 4, which is 12, which is an even number. So obviously even numbers can also be shown. Now what is the condition on these even numbers such that they can be shown as a difference of two squares? The condition here, as you can see, is you will require at least an even gap. So for some k, it will be minus k minus, say for some k square, sorry, minus k minus some 2m square, which is, it should be even, the difference between k and this p, say this is p and this is q, then the difference between these two p and q should be even. Then only will it be p square minus q square will be even. So what this will prove is it will be 2m number of consecutive odd integers which are extra, which are left in k square. And because let's say for some 6 square minus 2 square, it will be and 1 plus 3, so 4 number are left, which is the difference between 6 and 2 is 4. So 4 consecutive odd integers are left. Now we can prove for any two consecutive odd integers, they will the sum of them will have a factor of 4. How we can prove that is because say 11 plus 13 divided by 2 will be 12. So any consecutive odd integers when added and taken average of, it will give the number between them, the even number between them, which has a factor of 2. And if we multiply this 2 over here, as it already has a factor of 2 into 2, it will always have a factor of 4. So the condition we have here is, if the number is even, it should have a factor of 4. So we come at two conditions: every odd number can be shown as a difference of two squares, and every even number with factor of 4. So now these two conditions we know for the difference of two squares. Now we have to find the number of contiguous subsequences which fall under these conditions. So for that, first I'll take the input, which is the number of test cases, followed by an integer n, which is the number of elements in the subsequence a. Now what this will help us do is, we've taken the input, so I will declare a few variables which I will explain to you the meaning of. First I have answer, which is obviously my answer to my solution. Then I have an list even, which is empty at the start, so a vector. And then I have another list which will be even 4, which I will initialize 0 for I in range n. What this does is, as I'll quickly show you, say it is parent 0 for I in range 6. It will create a list with 6 number of zeros. Now that I have this, I will start the first loop, which will run n times. Here I will check each member of A. So if A of I mod 2 equal to 1, say if the number I come across is odd, I will declare another integer here, cur odd, which is the current number of odd elements. So I will add 1 to this number here if it is odd. Now what I'm doing here is counting the consecutive number of odd integers. So let's say I hit an even integer, then what should I do with this? So let's say that I have x number of odd integers, 1, 3, 5, 7, 9, 3, 65. So how many are these? There are 7. So I will have each number itself as an odd contiguous subsequence, so that will be 7 itself. Then I have pairs of 2, 1, 3, 3, 5, 7, 9, sorry 5, 7, then 7, 9, 9, 3, 365, so which will be 6. Similarly every 3 I will select, which will be 5, then 4 for every 4, then I will consider 5, 3 until 1. So what that means is it will be x plus x minus 1 plus x minus 2 until 1, which is obviously easily you can show as x into x plus 1 by 2. So the chain of odd elements will x odd elements will have x into x plus 1 divided by 2 number of contiguous subsequences which are odd, because as soon as one even factor comes in, the product of this entire sequence becomes even, because odd into odd will be odd as there is no factor of 2 in either of these numbers, but as soon as a factor of 2 comes in, it will always be even, and even into even will always be even as well. And this even here will always have a factor of 4, because this has a factor of 2 and this has a factor of 2, so this will always have a factor of 4. This may or may not have a factor of 4 depending upon this number if it has a factor of 2. So now that we have found this, so every time I find an even number, I'll add to the answer cur odd into cur odd plus 1 by 2, as that is the number of contiguous subsequences we have. Now we also have to do a few more things when we find an even number. That is, we have to make the cur odd equal to 0, as the current chain of odd numbers has ended. We have to add the index to the even array, this list, sorry. It will keep track of wherever the even numbers are. And we also have to check if a of I modulo 4 equal to 0, that is the number itself has a factor of 4. Then in this even 4, we will make even 4 of I equal to 1. So for every I that has a factor of 4, it will be 1, else it will be 0 in this array. So it will be a binary array showing us which numbers have a factor of 4. Now we also have to do one more thing. Say the last element in the list is even, and before that we had a chain of odd numbers. Then it will be easy to calculate this sum. But if the last number is odd, then this it never goes inside this else condition later on, and we never get the sum of the last chain. So we'll add another answer plus equal to cur odd into cur odd plus 1 by 2. So now that we have found it for the odd numbers, now we have to find it for the even numbers. So how do we find it for the even numbers? I'll declare an integer here equal to len of even, which is the number of even elements in the array, and we'll have bef equal to 0. Now I'll explain to you what bef is later on when I reach the uses of this variable. So now we have to find wherever two even integers lie in the same range. So we'll take a loop from the second element to from of the even to e, the number of even elements. We'll take a1 as even of I minus 1. Actually, we'll take this as b1, and b2 equal to even of I. So these are the two even elements. In the first iteration, this will be the second one, and this will be the first even element. So what we have to do here is, say for a sequence 1 3 4 5 6 7 2 9, in the first iteration we'll come across 6 and 4, so the element would be the second element index, and this will be the fourth indexed element. Now we have to find the number of contiguous subsequences in which this subsequence lies. So as this is the first one, we don't have to worry about the previous even integer and the repetition of the sequence. So the number of ways this contiguous subsequence can be selected is the number of elements before it plus 1, which is 2 plus 1, into the number of elements after it, which is 3, and it will be 3 plus 1, which is equal to 12. So this subsequence can be selected in 12 ways. Now why this plus 1 comes is because the subsequence can also be selected without taking these 2 1 3 into consideration, and then it can also be selected with 3, then it can also be selected with 1. So that will and similarly from this side, like so, this and this, and also just with 3, just with 7, so that will total form 12. You can check the proof for this, but it is pretty simple, PNC. Now that we have this, then we come across in the second iteration, we come across 2, and the previous even is 6. So the number with this would be the number of elements after this, which is 1 plus 1, and then the number of elements before it, which is 4, and then into 4 plus 1. But why this would be wrong is because it will be 10, but for example it will also consist of this subsequence which has already been selected in this one, 12, and also it will consist of this which is selected, and similarly every time we hit 4, that subsequence has already been selected. So what we have to do is select the subsequences in this range. So rather than have 4 behind 6, we'll have only this 5 behind 6, which would be 1, because every element before 4 and so have been accounted for in this iteration. So what this before that I declared here is the index of the previous even element, after which we have to take the following elements. So for this, rather than 4, this becomes 1, which will have just 4 contiguous subsequences, which would be 2765, 2765 and 9, and then also 9276. So that will be 4. So total number here would be 16 plus whatever the chain of odds is. Here it is 2, and also 9, and then 7, and then 5. Now how do we code this? I have declared here even of I plus 1. So first we'll add to the answer plus equal to n minus b2, that is the number of elements after that. So we'll always take it to the end when we're considering after, but when we're considering before, we have to keep in consideration the even number before that. So this would be the number of elements before that. Initially bef is 0, but next time we'll make before bef equal to a plus 1. A here is actually, sorry, b1. So we'll make it equal to b1 plus 1. So that will be as we'll have here in the 4 1, we'll have it as here. So it will only consider till 5, which will be 4. Now that we have this done for the even numbers, we are not done yet, because an individual number can also be a factor of, can have a factor of 4. So we'll check if even 4 of I equal to 1, that is, it has a factor of 4 in it, as we had done it here. If it has a factor of 4 in it, we made even 4 of I equal to 1. So if it is equal to 1, if I is equal to e minus 1, that is it, if it is the last element, we'll just add, we'll have af, which is elements after equal to n, which is the last element will be n, else we will only take it into consideration until the next even element. Because for example 4, if we take this entire range of 4 into consideration, we will have a result such as we will have 4 5 6 again, and we'll have 4 5 6 7 again, but we only want to consider this range. And if say we add an 8 here at place of 2, we'll only consider this range, that is before and after till the next even number. If this was 10, then we will only consider it till here. So if it is a multiple of 4, we'll take this range which will have the even number, and all we have to do is see the number of elements after it till the next even number, and the number of elements before it till the previous even number. Now if it is last till the next even number will be there will be no even number, so we'll take it till n, else we will have af equal to even of I plus 1, that is the next even element. Now as we had considered 6 5 4, we'll similarly just consider 8 as a subsequence which has 4, this had 4, and then we'll see the number of elements before it till the next even number, and the number of elements after, which is 1, so it will be 1 plus 1 into 1 plus 1, which would be 4. So we'll code that answer plus equal to af minus b1 b2 sorry and b2 minus b1. This will be the number of elements if an element already has a 4 in it. Now what we haven't checked here is if the number here has 1, because we haven't checked for the first element if it is a factor of 4, because we started from the second element. So we'll have to add another case here, that if even 4 of 0 is not even 4 of 0, even 4 of even of 0, that is the first element, equal to 1. Before that we also have to put in another condition, if e is not equal to 0, that is it does not have 0 even elements, because then this would give a runtime error that even of 0 would not exist. Now that we have put this condition, if e equal to 1, that is that it has only one even element, then answer will be even of 0 plus 1, because bef here will always be 0. We'll always take it from the 0th element till the last element, because there is no other element here. That will be the number of elements after it plus 1, and that will be the number of elements before it plus 1. But why we are putting this if e equal to 1 is because in the next one we'll take it till the next even number that we find. Even of 0 plus 1, this will remain the same, but this will, rather than n, become even of 1 minus even of 0. And if we had just put this and it had only one element, we would get a runtime error, as even of 1 would not exist. And that will be your answer for this question. So what we did from the start, I'll just explain it again. We first found the chain of odd numbers, and we added all the contiguous subsequences of that odd number into the answer. Then we found the positions of the even number, and which even number is also divisible by 4, as that can be a difference of 2 squares. Then from the second number we made the positions of the previous two even numbers, that is I and I minus 1, and then we added the contiguous subsequences that consider that before, rather than repeating this, like for example for 8 and 6, rather than repeating for all the 4, 3 and 1s, we took it from 5 till the end, and for the next one we would take it till 7 from the end. So that's what this def here was for. So now we find the number of elements after the second occurrence of the even element of even of I, which will be n minus b2 plus it will be plus 1 because b2 is 0 based indexing, so the last element will be at index n minus 1, so the number of elements after it is 0 and it will give output as 1. and this is the number of elements before it till the previous eventh element. Now the case missing here is if the element itself is a divisor of 4. Now why we are taking it till the next even element is because we already accounted for all cases that include 4 and 6. So all we have to do is before the 6 until the previous element, as we would have already accounted for. If this was 2, we would have already accounted for all 2 to 4. So for this one, it would be one element after and one element before. So it will be 1 plus 1 into 1 plus 1, which will be 4. Then we are only missing one last test case, which is if the first element is divisible by 4, as we are starting here from the second element. So we'll check for that. The number of elements after it, if it is the only element, would be n minus even of 0. Otherwise, it would be even of 1 minus even of 0. And this here would be number of elements before. So now we have counted for all test cases. This here I had written I earlier, it will be even of I. So there could be a couple of errors in the code as I'm writing it on the spot, but logically everything is correct. So try to write your own code rather than copy. And now as we've accounted for all contiguous subsequences, you can print your answer, and that would be your answer. So the next question is ready bitwise. Now it's a little difficult to explain this question, so I would recommend that you go through the problem statement once before hearing my explanation. That will make it a little bit easier for you to understand. Basically, you're given a string L where each operand has been replaced by the character hash. Hash here is operand, which is the value. There is x and y, for example. So x has been replaced by hash and so has y. We're given 3 operators, AND, OR and XOR. I'll explain to you what each of these are. I assume you already know about it, but I'll still go over them. So now we're given the definition of what a valid expression is. Either it is a single term hash or a string in the format expression 1, operator expression 2, and that will be inside brackets. So the first thing this clears up, the definition of what this valid expression is that we do not need to know about the priorities of AND, OR and XOR, because the priorities does not matter as all of these are within brackets. As they will be bracketed, you would not need to look at which operator to do first. For example, we have an hash XOR hash and hash. This is not a valid expression. You cannot have this possibly in the input. What you can have in the input is something like this. It will be bracketed and you will know which operator to use first and which brackets to open first. Okay, so now going back to the question, you have to find the probabilities with which expression obtained after substituting each character hash evaluates to these values. Each character of hash in the string L will be replaced by one of the characters 0, 1, A and A, where big A is negation of small a. That is, if small a is 0, big A will be 1. If this is 1, this will be 0. And it's uniformly and randomly and independently. That means for one hash, the probability that it is replaced by 0 is 1 by 4. So for 1, it's 1 by 4. And for A and A is capital A is also 1 by 4. Okay, so now we have to find out the probabilities that after all these operations we get 0, the probability for which we get 0, the probability for which the expression is 1, the probability for which the expression is small a, and probability for which the expression is big A. So we have to show this as a fraction p by q, where p and q are integers and q is co-prime with 99982443553. We have to take in modulo this. You should compute p into q inverse modulo 998244353. So from here on I will be referencing this as mod. At first glance the question is a little confusing because the problem statement is sort of difficult to understand, but the important part here is it will be bracketed up and you would not have to worry about the priorities of the operator. So for this first one, let's try to find the probability. So I'll start with OR. Now OR function's truth table is, you probably know it, 0 0 gives output 0, 1 0 gives output 1, 0 1 gives output 1 and 1 1 gives output 1. That is, if a single bit is 1, the output will be 1. If all bits are 0, then only will the output be 0. So we have to find out the probabilities for 0, 1, A and capital A from for OR. Now let's see in the cases for this operation, hash or hash. So for this expression, now we'll be finding out the probabilities. Okay, so let's see in which case hash or hash is 0. So this hash has all values 0, 1, A and capital A, 1/4 probability for each, and so does this. So 0 will be in the case probability of first hash is 0 into probability of second hash is 0. Right, first I'll explain in simpler way that only when both elements are 0 will we get 0 as the output. Now we need to know will 1 be the output. So 1 will be the output when a single bit is 1. So we'll have 1 comma 0 comma 1 comma A comma 1 comma capital A comma 1 comma 1. So when the first is 1, it will always definitely will be 1, and similarly when the second operator is 1, we will also have 1 as the output. So these are all the cases which will have 1, but there are also 2 more cases for this, which are A and capital A, because at least one of these values will always be 1. Exactly one of these values will always be 1, because if small a is 0, then capital A is 1. If small a is 1, then capital A is 0. So similarly, this will always be 1 as well. So these are the cases for 1, which are 9, I believe. Yes. Now we have the cases for small a, which would be a comma 0, because if small a is 1, then a1 or 0 is also 1. If this is 0, then the output is 0. So the output will always match a. And it will also have another case 0 comma a. Now I know these symmetric cases may be seeming similar to you right now, because these two have the same probabilities, but in the question we will arise at problem when this has a different probability for a and this one has a different probability for 0. So at that time you would have to compute these separately. And there's also one more case, which is a comma a. And similarly for capital A, you would have same cases as small a, just small a replaced by capital A. So these are all the cases for OR. So here you will see O is in 1 case, this is in 9 cases, this will be in 3 cases, and so will this. Now we'll move on to AND. So for AND, we'll have 0 a lot more times, because the truth table of AND goes 0 0 is 0, 1 0 is 0, 0 1 is also 0, and 1 1 is 1. That is, when all bits are 1, it will be 1, else the output will always be 0. So we'll start off by analyzing for each. We'll have 0 equal to when we have 0 comma 0, we'll have 0, and similarly whenever we have 0 in any position, we will always have 0, because even if one bit is 0, it will always end up in 0. So I'll just write down the cases for this quickly. And similarly the two cases for which OR was 1 will give 0 in this, because at least one of these bits will always be 0. For 1, this time there is only one case, which is 1 comma 1, when all bits are guaranteed 1, then only it is 1. So you can maybe seeing a trend here that A and capital A will have again the same cases, which will be 3, but they will be a little different, which will be A comma 1, 1 comma A, and the last case here would be A comma A. Similarly for capital A, so these are all the cases for AND. Now we'll move on to XOR. Some of you may not be familiar with the XOR operation, so I'll go over the truth table quickly. It is 0 0 is 0, 1 0 is 1, 0 1 is 1, and 1 1 is 0. That is, when both the bits are same, it will give 0 as the output, and when both bits are different, it will give 1 as the output. So that is what XOR basically means. Now we'll see the cases for 0. So when they're similar, when they're same, it will always be 0 when both bits are same. So we can easily see the cases for 0, which will be the 4 cases in which bits are same. Now for 1, it will be when both cases are different. So in 4 cases again, they will be different. The other 2 cases are A and capital A. These two will always be different, and capital A and A. Now for A, 0 XOR A will always be A, because if A is 0, then they are both same, output will be 0, and if A is 1, then they are both different, output will be 1. So similarly we'll have this, and then we will also have capital A comma 1. So 1 XOR A will always be capital. What we mean by this is capital A is 0, then this XOR both will be different and the output will be 1. If capital A is 0, small a will be 1, and similarly if this is 1, both will be same, so the output will be 0, and if capital A is 1, small a will be 0 as it's its negation. So similarly this, and now similarly for capital A we'll have same cases as small a. So yeah, capital A's probability will always be equal to small a's probability, because they're basically two operators which will have symmetrical values. So now that we have all the cases, we need to find the probabilities for each. Now how we find the probabilities is by solving the innermost bracket first and then moving outside. Right, here are some examples. 2 hash, all probabilities are same because all the probabilities are 1 by 4. In this and the probability of 0 is high, the probability of 1 is low. You are not able to see properly in this because we are using p into q raised to the power minus 1 modulo. So I will explain to you how to calculate this as well when we get to that point. So now that we have the cases for which XOR and OR work, we can easily find this probability. The difficult part comes in solving the brackets. So in the editorial, the way to solve the brackets is given as a binary tree, as whenever the priority of the brackets increases, you go deeper into the tree and you solve from the leaf to the root node for the probabilities. But I have done my answer using stack implementation of postfix expression, which most of you are probably already familiar with. So this is my code to convert a infix expression to a postfix expression. I found most of this online and then made the changes that were required in the question. So here I have converted my infix expression to postfix expression, and then what I have done is, if I find a hash in my postfix expression, I have added 0, 1 or whatever value of p is to that expression. What that allows me to do is, here this will be the postfix expression of this. So as you can see, we do not need to worry about the brackets. First we'll solve the XOR operation, then on the resulting probabilities of the XOR expression we will form the AND expression. So what this will give me in postfix implementation is 0, 1 XOR 2 and. So what I can do here is solve for the probabilities of 0, 1, then XOR those, and then whatever probability comes I can apply AND on that. Now I'll make this probability list which contains 1 for I in range P, that is the number of hashes I find. P here is the number of hashes as I am incremented wherever I find a hash. So the probability initially of every one of them is 1. So we'll have 1 in the numerator at all times. I can also make a power array that denotes the denominator, which will be 4 raised to the power 1 at the beginning for all, and I will increase the power here as I do not need to again calculate 4 raised to the power 3, 4 raised to the power 4, etc. So I'll just keep it at 1, 2, 3, 4, etc. Now what we'll do is we'll make a def evaluation function. Now what I need in this function is the posterior expression, the probability list, and the power list, which I'll name PO because it's a clashing inbuilt variable power. Okay, so the first thing we need to do is I need to iterate over post, and if I find an operand, I will make a stack here which will be empty at the beginning. So if I find an operator, let's say it is OR, so I will now compute the probabilities. Now in a stack I will take note of the top two elements. So first element will be stack of -1, which is the last element, and the second element will be stack of -2. So these are the last two elements. So first we'll calculate for the probabilities of 0. So for the probabilities of 0 I will initialize a variable for 0. Now we'll take a look at the cases we made. So for the first case, 0 will come in OR when both the elements are 0. So as there is only one case, we will make probability first 0 into probability of second 0. As this is the only case, we'll now move on to the probability of 1. So the probability of 1 is first we have the probability that the first element is 1, which will be this. Now the cases are a lot, so I'll try to simplify it a little bit. The sum of when the first element is 1, then we look at the sum of the probability of the second element in its entirety, because all the other elements, that is 0, A, capital A and 1 are also there. So we'll do this, do sum of probability of second plus when the probability of second is from the second element is 1. So the probability of second of 1 into the sum of probability of first. But here a case will be repeated when both of them are 1. So we'll subtract the probability of first of 1. Now we have two other cases, these two. So we'll quickly do this with plus probability of first A, second is A and the third is capital A, which so similarly it will be plus probability of so this will be the probability for 1. Yeah, as you can see it's pretty big. Let me make sure I made no error here. So for the probability of A, now we will find out there's 3 cases. So we'll go probability of first is A, which will be 2 into probability of second is 0, as that was the first case here, a and 0. We also have 0 and a and a and a. So we'll have plus probability of Then similarly for capital A, I will denote capital A by B because I don't really like making my variables in capital letters. So the probability of capital A, what we find is wherever you find 2 in the above 1, you convert it to 3. Now we'll look if the operator is the AND operator. Before that, actually, we'll make the probability of second equal to 40, 41, 4a, 4b. Now that we have changed the probability of second, we'll pop the first one out as we do not need its probability. We also make because they're getting multiplied. Then we'll pop from the stack. This will remove the first element and we'll only have the second element. So I've finished the rest of the code similarly by the table that we made here. For OR, this was the probability I had written down. For XOR, these were the probabilities, and for AND, sorry, and for XOR, these were the cases. So here is my code for that. This is for XOR. I made one small change. I simply made first the probability of enter stack of -1, so I did not have to again and again access probability of first of 0. I could simply access first of 0. And I also had to convert this to integer of these as they are string values, and that would have given a runtime error. So now once we have that, if it is not an operator, that is not XOR and OR, I will simply add it to the stack. I have returned the stack of int of stack of 0, but this will always be 0. I will show you why. Say we have some operation such as 0, 1, XOR, 2, 3, and OR. This is the postage expression, let's just say. Then first we'll add 0 to the stack, 1 to the stack in the second iteration, and then we'll XOR the probabilities of these two. That will mean that I push pop out a 1 and this now goes into the stack. So this is what we have remaining. Then 2 and 3 are pushed into the stack and AND with the previous two elements. So the probability, I will update it in the probability of 2. I will pop 3 out and AND does go in. Then for the probability of OR, I will do the updated probabilities of 0 and 2 and all those probabilities, and in the end always 0 will be left. So my answer will be probability of 0. Before that I have to actually run the evaluation expression. I don't need this, as I said it will always be 0. So I'll run evaluation. I have to send in post probability and power, and Q will be 4 raised to the power 0. Now how we will solve this high power is binary exponentiation. So in Python there is an inbuilt function for that. So I'll simply use 4 raised to the power p of 0. Now what binary exponentiation does is, if you do not know, say I have to do 4 raised to the power 26, let's just say. So 26 in its binary notation is of the form 16 plus 8 plus 2, which will obviously give 1 1 0 1 0. So this is 26. Now what I can do is I can pre-compute the powers of 4, such as this. I can compute 4 raised to the power 1, 4 raised to the power 2, 4 raised to the power 4, 4 raised to the power 8. That is the powers of 2. So then all I have to do is add the 4 raised to the power 2 plus 4 raised to the power 8 plus 4 raised to the power 16. Right, because this can be 4 raised to the power 16 into 4 raised to the power 8 into 4 raised to the power 2. Now for a small number this may not look like a big difference, but for some very big number, if it is in binary notation which are already computed, we do not need to again and again compute the same number, same power again and again. So it will save a lot of time. It can be done in login. So now that I have found out q as the power of 4 raised to the power p0, now all I need to do is, as answer has 4 values, which are probability of 0, probability of 1, probability of small a, probability of capital A. So I'll iterate over answer, and then I have made a GCD function here, def GCD. So I will find the GCD of q and p, which will be I, let's just say. So gc equal to GCD of e comma q. So I'll make a new variable p equal to p by gc and q equal to q. As I need the value of q later, I will make a new variable qq. Now why I'm doing this is because for the answer you need to find out p into q inverse, and where p and q should have no common factor. So I've removed the GCD from p and q. Now how to find q inverse? That is the question. So q inverse, when q and mod are co-prime, you can find q inverse of the mod, which is written right here, simply as I'll show you here first. Q raised to the power mod minus 2 whole mod. Now again this will be done using binary exponentiation. So I will write here so I already have q, so all I need to do is mod minus 2 comma mod. So this will be q raised to the power mod q raised to the power mod minus 2 mod. Now all I need to do is print p into qq and modulo it. So this will be my answer. So let's give an example test case here. As you can see, these are the probabilities which match up with this. So the answer for this is correct, and that is how you solve the